I'm always gonna be there to like play devil's advocate, like, you know.
That's what your loved ones and your family is supposed to do. But yeah, my class is starting and I gotta go. Love you too, bro. Bye. Just letting everybody come in. I don't get why there's only 2 people. Class has started. I typically get more showing because of that. Oh. Exam 3. Yeah, when was that supposed to happen? Open up that calendar. Exam 3. That's this Sunday. It's due this Sunday. Today's the 4th. Yep. All of your homework for this section of the exam for exam 3. Homework 1, 5.1, 5.2, 5.4, 5.5, 5.6, 5.8, 5.9. They're all due on Saturday, this upcoming Saturday. And the exam is this upcoming Sunday. That's when it's due. So, and guess what? We have reviewed every section. You're taking it tomorrow. Wonderful. Taking it early is fine. If you want to do that, it's up to you. This class period will strictly be review. So, and it's actually optional. It's an optional class period. I guess that's why so many people are not showing up, because I only have 2 people in here, Albert and Isaac. Okay, so yeah, this class, we're not going over any new material. We're just going over the past material that I just mentioned. If you guys have any questions, let me know and we can start working. That's most likely why there's not many people right now. It's because it's an optional lecture, because it's a review lecture. So. Can we do some turning equations into graphs? Yes, let's do it. Okay. What kind of equation? You just want me to make something up? All right, I'll have several different kinds. I'll have a linear one, and then I'll have like a parabola, or maybe even a cubic. Yeah, I'll do 3 different kinds for you. Okay, so let's say we have a equation. Let's say we have a let's say we have y is equal to negative 2x plus 3. All right. Notice y is really a function of x. So why don't we graph it? The way we graph it is to create an f of x table. And what we are going to do is we're going to tabulate what the function is at various inputs and tabulate what the function spits out at various outputs. Okay. So I'll put like a -2, -1, 0, 1, 2. Let's see what the function equals at each of these points. So f of -2 is going to equal -2 times a -2 plus a 3. And that's -2 times, that's 4, +4 plus 3 is 7. All right, what is f of -1? This is -2 times the -1 plus a 3. This gives me a +2 plus 3 gives me a 5. What about f of 0? This is a -2 times a 0 plus a 3. That becomes 0 plus 3, which is just a 3. What is f of 1? This is -2 times 1 plus 3. That's -2 plus a 3, which is a +1. Then we got f of 2, which is -2 times 2 plus 3, which that ends up equaling a -4 plus a 3, which is a -1. All right. Now that we've tabulated and evaluated and have that list, we create our xy coordinates. We place our x values -2, -1, 1, and 2, which are our inputs into the function. And we already know what the outputs evaluate at. So we'll just plot it. So here comes 1, 2, 3, 4, 5, 6, 7. All right. So at -2, I go to -2 on x. I find +7 on the y, and I put a dot. Then I go to -1 on the x, +5 on the y, 1, 2, 3, 4, 5, and I put a dot. I go to 0, I find a 3, and I put a dot. I go to 1, and I find a 1, and I put a dot. Then I go to 2, and I find a -1, and then I put a dot. And then what do we do to the dots? We connect them. So we'll go all the way here and we'll connect them. Notice we get a straight line, and that is of no surprise because we had a linear equation. This is a polynomial, and the degree of the polynomial is 1. And so it's a linear equation with y-intercept 3, as you'd expect. Okay. And so we plotted it, and that's how you find the graph. Let's say, for instance, you want to know what is this location here. All right. Let's say you need to graph it and ask you what that location is. This location, if this is the y-intercept when the line goes through the y, this is the x-intercept. It's when the line goes through the x. But notice, how can we discover that, what that value is? We can do so algebraically. The x-intercept is precisely when the y value is 0. So we'll set y equal to 0. Notice that when y equals 0, we still have this negative 2x plus 3 over here. So we can solve for the x that causes this equation to equal 0, and we'll find what that x is. That x is going to be this value right here, this mystery value. So I'll add a 2x to both sides, and I get 2x is equal to 3. Then I isolate for the variable x by dividing both sides by 2, and I get x is equal to 3 halves. So this location here is at 3 halves, which is the same thing as 1.5. And look, it's precisely in between 1 and 2, minus a little bit of my not drawing to scale. If it was drawn to scale, it would be perfectly right there halfway between them. So that's how you find some x-intercepts. And the y-intercept we could discover because this was in y equals mx plus b format, mx plus b format, where negative 2 was a slope, the y-intercept was 3. So that's how you graph a linear function. Let's talk about graphs of another kind. Let's do another kind. Let's do a quadratic function graph. And also, guys, you could go to my YouTube channel, Professor Niazi. I also have more resources on this very thing on there, so I'll write it. Okay. So what about graphing quadratics? Let's be given a function f of x is equal to, let's say, negative 2x squared plus x minus 1. What does this look like when we graph it? Well, I don't know, but I know how to find the graph of everything. And that's a f of x table. So what we'll do is we'll pick some values to plug in into this equation and see what the function evaluates. So we'll pick our favorite values, negative 2, negative 1, 0, 1, 2, and we'll see what does this function evaluate at. All right. At these values. All right. So f of negative 2 is then our negative 2 times negative 2 squared plus a negative 2 minus a 1. So what do we end up getting? This is a negative 2 times a positive 4 after you squared negative 2 minus a 2 minus a 1. So this ends up becoming, this goes to negative 8 minus a 2 minus a 1. So that's negative 11. Over here we get negative 11. What is f of negative 1? We play the game again. Negative 2 times negative 1 quantity squared plus negative 1 minus 1. So this equals negative 2 times positive 1 minus 1 minus 1. So this equals a negative 2 minus a 1 minus a 1. So that's negative 2 minus 2. So that's negative 4. What is f of 0? F of 0 is negative 2 times 0 squared plus a 0 minus a 1. So this ends up becoming 0 plus 0 minus a 1. So what we end up getting here, it's equal to negative 1. What about f of 1? That's negative 2 times 1 squared plus a 1 minus a 1. So this ends up equaling a negative 2 times a positive 1 plus 1 minus 1. So this ends up, these two cancel. So this ends up equaling negative 2. So I'll go over here and I'll put a negative 2. What is f of 2? F of 2 ends up equaling negative 2 times 2 quantity squared plus a 2 minus a 1. And this ends up equaling negative 2 times positive 4 plus 2 minus 1. And this ends up equaling negative 8 plus 2 minus a 1. So it's -8 plus 1, which is -7. So once we have those values, now we can graph it. So we'll clear up some real estate so we can graph this. Here's our x, and here's our y. So we got -2, -1, 1, 2. And what are we going to plot? Well, this function has a lot of large negative values. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is -11 down here. So I go to -2, I find -11. And I put a dot. I go to -1, I find -4. 1, 2, 3, 4, I put a dot. I go to 0, I find -1, I put a dot. I go to 1, I find -2, I put a dot. And then I go to +2, and I find -7. 1, 2, 3, 4, 5, 6, 7 right here. And I put a dot. Now, what happens when we connect the dots? We notice we get this shape, a beloved shape to mathematicians. This is called a parabola. But usually, parabolas were opening up. What happens? This parabola is opening down. So that's because of the minus sign out here. That minus sign is flipping the parabola upside down. But now you know how to graph it, because the question was how to graph things. So that's an example of how to graph a parabola. But guess what? I'll give you some extra info. I'll give you a bonus one. I'll show you how to graph a cubic function. Why don't we graph a cubic function? How about f of x is equal to x cubed minus x plus 1? All right. What does this function look like? I know how to find the graph of every function. I create a table. We got -2, -1, 0, 1, and 2. Let's evaluate the function. What is f of -2? This equals a -2 cubed minus a -2 plus 1. So this ends up equaling -8 plus a 4, because the negatives cancel, and you guys know why, plus 1. So this becomes a -4 plus 1, which is a -3. So I go over here, I'll put a -3. What is f of -1? So that equals -1 cubed minus a -1 plus a 1. So this ends up equaling a -1 plus a 1 plus a 1. So these -1s cancel. So I just get this equaling 1. Put a 1 right here. What is f of 0? Well, that's just 0 cubed minus a 0 plus a 1. So this is just 1, and I put a 1. What is f of 1? Well, that's just 1 cubed minus a 1 plus a 1. This ends up equaling 1 minus a 1 plus a 1, which is 1. Put a 1. What is f of 2? F of 2. This is equal to 2 cubed minus a 2 plus 1. This ends up equaling 8. 8 minus 2 plus 1. So that's 6 plus 1, which is 7. I put a 7. And now we will graph it. So once we tabulate, first step is to tabulate your results at various inputs. Put in various inputs, compute the various outputs. Then step 2 is to do put the dots, and then step 3 is connect the dots. Here's x. Here's y. We got -2, -1, 1, 2. Then we got some outputs at -2. I find a -3, 1, 2, 1. I gotta make those look better. 1, 2, 3. I go to -2. I find -3. I put a dot. I go to -1 and I find a +1, and I put a dot. I go to 0 and I find positive. I go to -1, 1. I put a dot. I go to 0. I find a 1 and I put a dot. Is that right? Yeah. I don't think that's correct. Hold up. F of 0. Yeah, that's 1. Was f of -1 1? Did we mess something up? F of -1 is equal to -1 cubed minus a -1 plus 1. This is -1 plus 1 plus 1, which is still 1. This is that's weird. So the f of 0 is indeed 1. F of -1 is indeed 1 as well. Sanity check here. What? That's very odd. And to make things worse, f of 1 is 1. Oh my, I picked a really bad function here. Because it's not a function. You guys see that? I created something that's not a function because when you connect the dots, look. Well, I guess it doesn't disobey the vertical line test, does it? Oh. I guess it is still a function. No, that's fine. All right. Then at 2, we find a 7. 1, 2, 3, 4, 5, 6, 7. I go to 2, go to 7, I put a dot. And then notice that once we connect the dots, we get a cubic graph. So now you know how to graph cubics as well. The reason why I'm kind of feeling weird about this is because I feel like in between these two spots, the function's doing some weird stuff. But we don't have to know what it's doing there. We just got the inputs. And that's fine. Already subscribed. Woohoo! Make sure to like and comment and share and all of that. I'm getting used to advertising for it, but yeah. So that's how you graph linear, quadratic, cubic, anything. When you get your function f of x, create your table for various inputs, compute the outputs, and put a dot, and then connect the dots. I thought there was an issue, but there wasn't. There was no issue. I just thought that there was, but there's not. Did not mean to alarm you, but yeah, there's no issues. It's a completely fine graph. Good. Any other questions? Oh, we got some more people in here. Now it's Isaac. Oh, the other Albert left. So now it's Isaac, Kiana, Zoe, and Ashley. None from me. Got it. None from me. No questions? Okay. Anybody else have questions? This is an optional class, and we're just reviewing stuff. You say, hey, how do you graph equations? And I'll show you how to do it. You say, hey, how do you divide polynomials? And I'll do it. So basically, I can help you out with anything that you're confused about. That's what's going on today. I'll be right back. I'll let you guys think of your questions. I'll be right back. Okay, look it up. Good. All right, I'm back. I had to micturate. Who here knows what it means to micturate? Nope. Don't know what it means to micturate? I always like teaching students about that term because it's very funny. So right now, unless one of you guys has a kidney failure, micturition means, so unless you have kidney failure right now, you're all urinating. Because urination is a process of creating urine. Your kidneys filter your blood and they take out the uric acid and excessive salts and other biochemical byproducts that your body doesn't need, uric acid, stuff like that. And it sends it to your bladder, preparing for micturition. Micturition is the actual process of ejecting the urine outside your body. So when you hear people say, "Oh, I gotta urinate," that's dumb, because you're already urinating. Everybody is, unless they have kidney failure. What they mean is they have to micturate. How do you find the long end behavior? Well, before I even erase this graph, let's just talk about this graph. What is the long end behavior here, as Zoe asks? Is the concept of the limit. We take the limit as x approaches infinity of our function x cubed minus x plus 1. Notice that, you know that whole term, which one wins, numerator or denominator? is a trivial question indeed, because the denominator is just a constant 1. So clearly the numerator wins. And you guys know what happens when the numerator wins, right? The outputs become arbitrarily large. As you can see, this function is headed way up. The larger numbers you put, the larger the function gets, implying that the end behavior is it blows up to infinity. Now, Zoe, what about the limit as x approaches negative infinity of our function? Well, again, similarly, we got to divide it by 1. And if you look at the function, this is kind of cheating. You shouldn't have to graph functions to know what it's doing. But if you look at the function, it's clearly going towards negative infinity. And here's the reason why. If you input a negative infinity into something cubed, any negative number cubed still remains negative. So that's why your output should be negative infinity, because arbitrarily large negative numbers, upon cubing them, will result in a negative number. So an arbitrarily large negative input will result in an arbitrarily large negative output. So the end behavior here is that it goes down towards negative infinity for negative inputs, and it goes up towards positive infinity for positive inputs. Is there a function that you would like to analyze its long end behavior, Zoe, in particular? Or would you like me to come up with various examples? You can just come up with one. Okay. Let's do another example. What about if our function is equal to x over x plus 1? Well, actually, I want to modify it. How about we call it 4x over x plus 1? Actually, I want to modify it. What if we call it 4x divided by 2x plus 1? I just noticed Mr. Niazi is left-handed. I'm ambidextrous. The end behavior, look, right hand, as x approaches infinity of this function is like so. Take this out, switch to the other hand. Whoop. So who wins? Numerator or denominator? We notice that this is power 1. This is power 1. So who wins? Who wins? The denominator? No. The numerator? No. Wait, are they equal? Yes. I just said this is power 1, this is power 1. So the degrees are the same. This is a degree 1 polynomial, a linear polynomial. This is a degree 1 polynomial, a linear polynomial. So it's actually a tie. So what is the result? What is the long end behavior? However you put it. The end behavior. Recall, when it's a tie, no matter what, when it's a tie, the leading terms, the limit is the ratio of the leading terms, their coefficients. So the end behavior ends up equaling 2 for the limit as x approaches positive infinity. What about the limit as x approaches negative infinity? I'm not sure, but that's okay. It's okay to not be sure. Notice that, again, it's a tie. It's the same function. But because it's negative infinity, when you input a negative number into a first degree input, you don't square it to undo the negative. So it stays negative. So this ends up becoming the ratio before, but the negative of the ratio before. So what this is implying is that the end behavior to the right goes towards positive 2, and that the end behavior towards the left goes towards negative 2. So these are our horizontal asymptotes. Keep this. So what is our vertical asymptote? Well, we discover what the vertical asymptote is by setting the denominator equal to 0 and solving for x. Because it is precisely at that point that the function cannot evaluate to a number that makes sense, because you're dividing by 0. So notice that when we set the function equal to 0 and solve for x, we get that x is equal to negative 1/2. So the vertical asymptote is x is equal to negative 1/2. Because you subtract the 1 and divide by 2, you get x is equal to negative 1/2. So now with this information, we can have a way of graphing it and knowing what it looks like. We know that there's going to exist a horizontal asymptote at 2, at y equals 2. And we know there's going to exist a horizontal asymptote at y equals negative 2. And furthermore, we know that there is going to exist a vertical asymptote at x equals negative 1/2. One, negative 2, negative 3, 1, 1, 2, 3, 1, negative 1. All right. So we have the asymptotes, but what does the function look like? Well, we know it definitely has these asymptotes, but what does the function look like? To again get some more practice on what functions look like. After computing their end behavior, and after computing the vertical and horizontal asymptotes, which the horizontal asymptotes is what gives you the end behavior. The vertical asymptote is what you discover by setting the denominator equal to 0. We find the rest of the information out by creating a f of x table. And we'll make sure we never plug in -1/2 as an input, right? Because we already know it's not going to work. -1/2 won't work, so let's not plug it in. Let's pick like, a -2, -1, 0, 1, and we're not going to pick 2 either. No, 2 is fine, but the output 2 is what's not allowed, okay? So now let's do some evaluations. What is f of -2? Oh, that's just a 4 times the -2 divided by 2 times the -2 plus 1. See, what I'm doing is I'm just replacing every x with a -2. This evaluates to -8 on the top, -4 plus 1 on the bottom. So this evaluates to a -8 over a -3. So the negatives cancel, so I get positive 8 over 3. What is f of -1? So this is 4 times the -1 divided by 2 times the -1 plus 1. So this ends up equaling a -4 divided by a -2 plus 1. All right. This ends up becoming the -1 on the denominator, and the negatives cancel, so this becomes positive 4. All right. What about f of 0? So f of 0 ends up becoming 4 times 0 divided by 2 times 0 plus 1. This ends up being 0 divided by 0 plus 1. So this becomes 0 divided by 1. Oh, but that's 0. Remember, 0 can exist in the numerator. 0 just can't exist in the denominator. That's when things are really bad. In the numerator, every time you have a 0 in your numerator, the overall fraction becomes a 0. So zeros can exist in the numerator, but not the denominator. Interesting. What about f of 1? So that's 4 times r1 divided by 2 times 1 plus 1. So this becomes a 4 over 2 plus 1. This becomes a 4 divided by a 3. So what is f of 2? We got f of 2. That's equal to 4 times 2 divided by 2 times a 2 plus a 1. This ends up equaling a 8 over 4 plus 1. This ends up equaling a 8 divided by a 5. All right, I go to -2. I find a 8 over 3, and I put a dot. What is 8 over 3? Well, 3 can go into 8 once, twice, with the remainder of 2. So it's a little over 2. So a little over 2 is going to be, if this is 1, this is 2, it's going to be like around right here. Put a dot. I go to -1, I find a 4, and I put a dot. There's 1, there's 2, there's 3, and there's 4. I go to -1, I find a 4. I'm going to put a dot. I go to 0, I find a 0, I put a dot. I go to 1, I find a 4 over 3, which is around like 1 point something, a little over 1. I go to 1, I find 4.3, and I put a dot. I go to 2, I find 8 over 5. It can go in a little bit. Yeah, it goes like a little, so it's like right there, a little over. It's over 1. It's almost at 2, but not quite. And what you do is you connect the dots. And you know it's going to have end behavior like that. And you know it's going to asymptotically approach that. And then over here, you know that it's asymptotically going to avoid the horizontal. And then it must also avoid the vertical. So our function is like so. And you know what? I can add some origins to it to make it look distinct. Maybe I can add some squigglies too. Is that satisfactory? Who asked the question again? Oh yeah, end behavior. Whoever asked it, I forget who asked it. Is that satisfactory? Yes, thank you. Okay, you're very welcome, Zoe. Does that answer? Okay, that answer your question. That's real good. Any other questions? You guys have a question? If you do, just type in yes, so I know you're just like thinking of it, or type it, or getting ready to input it, or something like that. You guys there? Excuse me. Is anybody there? Isaac, Kiana, Zoe, Ashley, anyone home? That's all I had. Okay, good. Yeah, I just in here. Okay, good. I just wanted to make sure you guys were still there. I was wondering if you guys have any questions. Because I would love to answer them. Nope. All right. I respect that. Is there anybody that does have a question? So Zoe's good. Kiana's good. What about Ashley, Isaac? You have any questions? Ashley and Isaac, you guys have any questions? You guys have any questions? I say I'm going into the grade book. I got to deduct some points from students that ignored the teacher. Open this grade book, deducting points. Or disrespect. I'm just kidding. Maybe they're on Zoom, but they have to go to the bathroom or something. See, I prefer in-class stuff, but you know, online's cool too. But one thing as cool in class is I can see your faces if you have any questions, or if you're confused, I can just tell it from looking at your faces. Also, I can tell if you're there or not. Are you guys here? Zoe and Kiana? Are y'all still here at least? You are okay. Well, this is a lot. I'm here. I'm doing the homework. Okay. All right. Well, I'm doing the homework at the same time too. Aren't y'all just some two peas in a pod? Well, if there's no further questions, I'll see you guys same time next week. All right. See you guys later then. See you later, Kiona. See you later, Ashley. Oh, Ashley, you're actually here. You not have any questions? See you later, Zoe. Okay. Well, see you guys later then.